Hello, everyone. Thank you for joining us today. My name is Sean Sullivan, and I will be your host for this Technology Gateway webinar on NASA Langley's long-endurance vertical takeoff and landing unmanned aerial vehicles. Our presenter today is David North. Mr. North is the Unmanned Aerial Systems Section Lead in the Aeronautics Systems Engineering Branch at NASA Langley Research Center. His current areas of research are unmanned aerial system design and advanced prototyping techniques for aeronautics and space systems. Recently, Mr. North has managed the GL-10 VTOL UAS project, the Mars Electric Reusable Flyer project, and the Rapid Packed Urban Air Mobility UAS project. Following David's presentation on the technologies, my colleague Jennifer Viudez, a licensing specialist at NASA Langley, will be giving a short presentation on how to license NASA technology to your business. Now, before we get started, I want to point out that your microphones will be muted throughout this presentation. So, if you have questions for David or Jennifer during their presentations, please type them into the chat box, and we will answer them during the Q&A session at the end of today's webinar. So at this point, I'm going to turn it over to you, David.
Hi, everybody. This is Dave North, and happy you could be here today for this webinar about our long-endurance VTOLs, two of them that we've developed here at NASA Langley. And I will just start in. The two VTOLs that we've developed are, the first one's called the Grease Lightning, or we call it the GL-10 because it has 10 rotors, and the second one is a 3-rotor long-endurance VTOL called the Trifecta. Okay, so why did we develop these VTOLs? And the two big problems are, the first problem that we faced with the VTOLs and the requirements that we wanted to develop or had for developing these VTOLs was multicopters just don't have enough flight time and range. Most big multicopters now in the range of 20 to 55 pounds have roughly a half an hour, maybe 45 minutes of flight time, but not enough time to do a lot of the missions out there like surveying and assessment of infrastructure and things like that. A lot of these multicopters just don't have the capability to do those missions. And then the second big problem that we address with these vehicles is the ground infrastructure currently for forward flight vehicles or CTOL vehicles is really large. These vehicles, even ones that are small, like in the 55-pound range, require big catapults. They require catch nets, catch wires, a lot of ground infrastructure and crew to run those ground infrastructure items. So with these VTOLs, we address that concern because the vehicle takes off in hover mode and then transitions into forward flight, and then again transitions back into hover mode for the landing. So no ground infrastructure like catapults and catch nets are required. So this slide is a little bit closer look at the two vehicles. At the first vehicle, the Trifecta vehicle, and on the left-hand side, the figure shows the vehicle in the forward flight configuration. So the rotors, the front rotor is facing forward, and then the back rotors have been stowed in their cruise configuration. So it looks pretty much like a regular airplane in its forward flight mode. And then in the right-hand figure, it's shown in the hover mode. The front rotor has tilted up 90 degrees, and then the back rotors are in action, and they are RPM controlled and providing hover controllability. A little more detail of this: the Trifecta is a series type hybrid. It's a parallel hybrid. The GL-10 is a series hybrid where the electric generator and the internal combustion motor are running in parallel to each other. So the internal combustion motor in the Trifecta is running the front rotor, and then the back two rotors are run off a battery which is supplied by the generator. some of the characteristics of the trifecta. It's a VTOL. It's a hybrid electric VTOL, so it has a liquid fuel motor and then 2 electric motors. It is roughly three times more efficient than a typical multi-copter and 3 times faster than the multi-copter, because it does get into wing-borne flight mode when it's in forward flight. So that allows a 50 times increase in endurance and range. And our initial requirements for these hybrid electric vehicles was a 24-hour mission with a range of 1,300 miles. And that is for the full-scale version, a 20-foot span vehicle. We actually built 50% scale versions of both the GL10 and trifecta. And these pictures on this slide show the trifecta, the 50% scale trifecta that we built. These 50% scale prototypes that we built are all electric. They were mainly focused on getting the controls technology worked out for the vehicles. And then we have not built the 20-foot full-scale versions of the hybrid electric, but that is in our long-term plans, is to build those full-scale prototypes. Okay, moving on to the GL10. It is a tilt-wing, tandem-wing VTOL, so both the wing and the tail tilt 90 degrees, and on the front wing there are 8 electric motors, and on the tail there are 2 electric motors. There are actuators that tilt both the wing and the tail relative to the fuselage. And again, this is a series hybrid electric, so all of the motors are electric, and they are driven off of a battery pack, which is kept topped off by a generator. So in cruise mode, on the left-hand side, 8 of the 10 propellers fold back against the motor nacelles, and only the wingtip motors are left rotating. So that allows for a really cruise-efficient configuration with low drag. And then in hover mode, all 10 rotors are used for flight control. And then yaw control is with blown ailerons underneath the wing rotors. Again, the GL10 has about the same characteristics as the trifecta. It is 3 times more efficient, 3 times faster than a multi-copter, and it has roughly 50 times the endurance and range of a multi-copter. And those pictures below are of the actual 50% scale model that we did extensive testing on here at NASA Langley. Okay, what types of applications could you use these vehicles for? You could use it for agriculture surveillance, where you need to have a vehicle up and not landing every 30 minutes, where you wanted to survey large amounts of land area. You know, if you're doing sort of a lawnmower pattern shown on the upper right-hand figure there, this vehicle would work very well for that. You could do highway and bridge inspection, like if you had to fly out a distance and survey a road and then you wanted to pause and get better imagery of bridges or any infrastructure for transportation. You could do that with these types of vehicles. Package delivery, it's perfect for that. You take off vertically, fly out, deliver the package, and then take off vertically again and fly back to the initial location. They could be used for pipeline inspections, forest and land management, search and rescue, border patrol, where you need a vehicle to maybe perch and stare for a while. And then finally, a lot of work is being done in the urban air taxi arena, and these vehicles could potentially be used and scaled up for autonomous urban air taxi applications. All right, so diving into the requirements that we use for both of these projects, the customer that we originally designed these for wanted a very small footprint for the takeoff and landing zone. The requirement was 20 feet by 20 feet to land in and take off. The landing accuracy on the outbound landing, or at the end of the outbound leg, had to be pretty accurate. So 1.5 meters was the requirement there. So we designed the vehicle so that if you had a sensor system that could do that, the vehicle could do that. We didn't actually design that landing system for our prototype. The loiter mission for these vehicles was the sizing condition. So they're really designed for low or high liftover drag. And that was really the driving function for the design of these vehicles. There were some other requirements that drove the design, like a 100-knot dash speed, and then there were other parts of the mission where it had to fly at a fairly high altitude, up to 21,000 feet. The vehicles were designed for autonomy, so they were to be flown with satellite communication, and no operators were required for most of the 24-hour flight, or actually for the full-scale vehicle, we envisioned no operators at all, so they would fly the whole mission autonomously. Some of the other requirements that we did meet with the 50% were low noise. The GL10 vehicle in particular has a very high frequency noise signature, which makes for a signature that doesn't travel very far. We noticed when we were testing the vehicle, you could stand about 100 yards away and you could still hear the vehicle, but you kind of had to listen for it very carefully. So the GL10 in particular has a very low noise impact signature. So that's the last two bullets on that slide. Some other characteristics of the full-scale vehicles: they were to be 264 pounds, wingspan about 20 feet. The fuselage length on those full scales was to be around 11 or 12 feet, and the wing loading fairly low at 9 or 10 pounds per square foot. Some other things, pretty good L over D, 20, which is kind of unusual for a lot of small UAS. The VTOL power required was roughly about 8 or 9 times the loiter power, and that's how you achieve the efficiency. VTOL power was about 22 or 23 horsepower, and then loiter or cruise power is 3 horsepower. Okay, just a summary of what we've done here at NASA in developing these vehicles. We've done extensive flight testing of the GL10 and of the trifecta. The GL10 prototype that we built was a 50% scale, all electric version. And then we did a lot of testing at 35% scale of the trifecta concept. We're currently using a COTS VTOL flight controller. We are currently working on in-house versions of that controller, but right now we are using COTS flight control with publicly available firmware, VTOL firmware, to fly that. So the next phase of development would be the development of the hybrid electric propulsion system, and we have acquired that and are planning on developing that, and first at 50% scale and then later at full scale. And that's it. Oh, there's a video here we'd like to show you guys. This is a little snippet of the GL10 video that's available online. If you just search online, you can find the longer video of the GL10 testing. Just search for NASA Grease Lightning. Is there any audio on? I'll just say a few words about the video as it's running here. So Again, this is the 50% scale, all electric version. So that was showing the transition from a hover mode into a 50% transition. So you're seeing it right now in about a half transition. It's halfway between hover and forward flight. And then a few seconds later, you'll see it transition into full forward flight. So right here is the transition from and you can see it from an onboard camera to full forward flight. We probably have about 100 hours of flight time on this vehicle, so maybe 80 to 100 hours, something like that. All right, and then this slide just shows the two patent and then the patent application for the trifecta. And those numbers are below each figure if you want to go look at those in detail. And I believe that's it.
All right. Thank you, David. So we have received a number of questions from you all so far. Keep sending those in right into the chat box, and we will get to them shortly. But first, Jennifer Viedez, my colleague, who is, again, a licensing specialist here at NASA Langley, is going to give a quick overview on how you can do business with us through technology licenses.
Thank you, Sean, and I'm happy to be here with everyone today. Hopefully everybody's having a good afternoon or morning wherever you are. We are going to change gears here a little bit and sort of move from the technical part of the conversation to, as Sean said, how to license a technology here from NASA Langley. This is a logo chart, and the point of it is to let you know that we have many different licenses with multiple different types of organizations, everyone from small businesses of 1 to 2 people all the way up to large businesses like you see on the chart, like Pepsi. We have licenses with local businesses and across the United States. We also engage in some international licenses, so that is also a possibility. Hopefully you found your way here today, possibly through our website, which we're very proud of. The technology.nasa.gov is where all of our intellectual property and patents pending, are housed here on this website. Here at NASA Langley, at our particular site here in Hampton, Virginia, a lot of our mission work results in the following types of intellectual property, as you see here on the chart, which are advanced materials, aerospace applications, sensors, and detectors. Generally, the agency as a whole, all of the centers across the United States, categorize the intellectual property into the categories that you see below. So once you go to technology.nasa.gov and you click on materials and coatings, for example, all the intellectual property and the patents pending will come up and give you more information. We have different types of licenses that we offer here at NASA, and one of the first ones, and one of the generally the typical ones, is a standard commercial license. I've already mentioned that we do license, obviously, to domestic companies as well as international organizations. And the important thing to remember here that a standard commercial license is negotiated on a case-by-case basis. They really are not cookie cutter, and so people like myself as a licensing specialist work very closely with the licensee to discuss the technology, to discuss the business needs and the planned technology, the planned use for the technology, and usually based on the business plan, based on the actual technology that's being licensed. That's how we determine and come up with the royalty rates. People are always very interested in royalty rates. You'll notice that we have exclusive, partially exclusive, or non-exclusive. So that just means that you do have the option to license all the fields of use. So if a technology has multiple applications, you could exclusively license all of those applications, or you could decide to do something more partially exclusive and carve out a field of use that is more applicable to your needs. We also have a couple of different licenses. One is a startup license, and that is very appealing to startups. The important thing to know here is that this type of license is only available to U.S. companies and only on a non-exclusive basis. And whereas the commercial license that I just spoke of a moment ago does have an upfront fee, the startup license does not have an upfront fee, and there are no annual minimums for the first 3 years. So that really allows the small business to get up and running and keep the resources in its pockets, so to speak, and fees aren't due until the 4th accounting period. Generally, the businesses need to be in place for less than 12 months, and there are a couple other stipulations like having less than $2 million in assets, as well as having less than 50 employees. But if you have any questions about any of these licenses, please feel free to contact us. The evaluation license is also something that's attractive because maybe you're just not ready to enter into a full-blown commercial license and you're not sure if the technology is what you want or it's going to fit your needs. You have an option to enter into an evaluation license, and it says just what it says on the chart. It gives you a chance to try it before you buy it, and those are put in place for 1 to 2 years on a non-exclusive basis. And you can do everything with an evaluation license that you can do with a commercial license, except you cannot make sales. And that evaluation license has a one-time fee of $2,500. So the first step of licensing a technology from NASA is to submit your application. And you can do that by going to technologygateway.nasa.gov. You do see an acronym on the right-hand side, ATLAS. The website, I believe you can also search, NASA Langley Research Center ATLAS, and you can submit your application electronically online there. We would need proof of your incorporation of your actual business with a financial statement, and as I mentioned before, a business plan, and your projected use of the technology and how much you think that it would take to get the product or service up and running. The negotiated terms are, like I mentioned, especially for the commercial license, we negotiate upfront fees, we negotiate the annual minimums, the royalty payment. The field of use, as I've already mentioned, the field of use is where the exclusivity, partial exclusivity or non-exclusivity comes into play. And the negotiated terms are also include the geographic locations for manufacturing and product sales. So the takeaway is the very first step is to submit your application and at least get started from there, and then you can begin speaking with our office and narrowing down and making this work for you. So generally, this is just a review of what I've already talked about. You would find the technology that would be of interest, of potential licensing interest, hopefully, for example, today's highlighted technology, VTOL. You would contact our office, which we will provide that information to you, and we will talk. We will have a lot of going back and forth. You will have a chance to possibly have a conversation with the inventor, to have some of your questions answered that way. All of your business questions would be answered through our office. You would submit the application, as I mentioned a moment ago. Our office would review it and make sure that you do qualify, and then the different negotiated points would come into play, like I mentioned, upfront fee, royalty fees, etc. We come to an agreement and you have an actual signed document, and we move forward and you've licensed, and we want to see you be successful. So I think at this point we're ready to accept some questions. Here you do see Jesse Midget's name as the Technology Portfolio Manager and how to get in touch with him. And certainly feel free to contact him after the webinar to ask any questions for follow-up. And thank you.
All right. Thank you, Jennifer. So we have received many questions so far. Keep submitting those, as I had said before. You can put them right in that chat box. If you have any questions for Jennifer about her presentation, go ahead and feel free to submit those as well. we'll be happy to answer those as we go forward. So we had a couple questions actually submitted before we started the webinar today through our email, and so I want to get to those first. And Jennifer, this one is probably for you. So if somebody were to license these technologies, what exactly do they get?
Right, that's a good question, one that we receive often. And you get the right to make, use, and sell what you see in the patent, or what you see in the patent pending. So it's really up to the company to have the expertise that it needs to be able to move forward to use the technology. Now, that being said, there are mechanisms that are in place where the company could potentially work side by side, for example, with Dave North, to try to get questions answered, to make further development. But basically, the answer is to be able to make, use, and sell a product or a service with some help on an as-needed basis from NASA as the mission allows and time allows. And there are other mechanisms that can be put into place, namely a Space Act agreement, which is just our document that allows us to partner with companies. I can certainly answer questions about Space Act agreements offline. I'm happy to do that.
Great. All right. So David, I think this one's for you. Do either of these designs of the aircraft, do they allow for the incorporation of solar panels?
I think you could put solar panels on these. They certainly wouldn't provide enough power needed for the complete mission. You might be able to power some auxiliary systems, but for primary power, you would need either the hybrid or hybrid electric, or if you were building a smaller scale version of it, probably battery powered electric. But it doesn't, these designs are not prohibitive of including solar panels. So I guess there could be scenarios where the vehicle is left to charge up the batteries with a smaller solar array, and then you've built up enough energy in the batteries to do the flight. But I don't think there's enough surface area on the vehicle to be able to make up the power required for direct solar power of the motors.
Okay. Jennifer, I think this one goes back to you.
Okay.
Have any licenses, exclusive or non-exclusive, been issued for these designs? Do you know?
Yes, I do know, and we do have some licensing interest in this technology. We've done a lot of marketing, and Mr. North has been very helpful in supporting those potential licensees. And I can say that it is not exclusively licensed, and it is certainly available to be licensed.
Great. And back to David. So has any special material or components been used to build these prototypes?
Nothing that's not standard aerospace prototyping materials. It's regular carbon fiber, epoxy, graphite, carbon fiber, fiberglass, even wood in some parts of the vehicles. And then we've even used COTS, electric motors, COTS, batteries. So there are a few parts that were machined at our machine shop here, but nothing that's out of the ordinary for standard aerospace prototyping.
So you're just talking about the cost controller. We've gotten a number of questions about that.
Right.
Can you talk about exactly which COTS controller the GL10 uses?
Sure, yeah. This will be a little bit surprising to everybody, but a lot of other companies have used this controller also, and it's a hobby grade IMU board called the KK2.1.5, and we're running a special version of the firmware called Open open aero VTOL. And again, these were all developed, both the board and the flight control system were not developed here at NASA. They were open source development. We did work a little bit with the developers to add some features, which are also now available in the open source firmware, but it's all off-the-shelf, publicly available hardware and firmware that we use to fly this vehicle. Now, we configured it, and there's a lot of settings in those controllers that it took a lot of time for us to dial in, things like feedback gains and leveling controls and allocation of power to motors, things like that. So it did take us quite a bit of time to get the settings right in that firmware, but the firmware itself is publicly available.
Great. So another question that's been very popular so far has been asking about the payload capacity for both of these vehicles. Can you talk about that a little bit?
That's a good question. Can we scroll back? I think for the full-scale vehicle, if I recall correctly, I think it was a 20-pound payload. I don't know if it's on that slide or not. Maybe not. I believe for the full-scale, it was a 20-ish pound payload, and then for our half-scale electric vehicle, it was a 5-pound payload. And those are kind of round numbers.
So the 20-pound was for the full scale?
For the full 20-foot span vehicle.
Great. All right. Moving along. So there's somebody who would like to know more about the Mars Flyer that I touched on when I was going through your bio. Is there any information out there that they could find or point to, or maybe that's something we follow up with?
We have a video out there that was published by NASA. It's I think the title of the YouTube video is NASA Engineers Propose Mars Flyer Concept or something like that. You'll find it if you type in NASA Mars Flyer. That technology, though, is not currently submitted for IP. That vehicle design is a well-established vehicle design that we didn't want to pursue, because there's nothing special about the design other than the application that we're targeting, which is Mars flight. But anyway, there is a YouTube video out there if you want to know more details about that. Yeah, it's called NASA Langley Engineers Propose Mars Flyer Concept, and there's a 5-minute or 4.5-minute YouTube video out there.
All right, but let's get back to the subject today, which is the 2 VTOL. But I just wanted to get that out there for that person. So you touched on this a little bit in your presentation, but can you go over the pros and the cons a little bit more of what these 2 VTOL UAS designs have over things like hybrid quads or flex rotor type UAS?
So over a hybrid quad, or I think we call them separate lift thrust, but that's probably the most popular type of VTOL vehicle. And if anybody's familiar with what's going on in the VTOL UAV market, about 95% of VTOL concepts out there are separate lift thrust. So it more or less looks like a mashup of a quadcopter and a regular CTOL UAV. So typically they have 4 rotors, 2 in front of the wing, 2 in back of the wing. One of the disadvantages of that type of vehicle is you have these booms and these rotors which are kind of draggy, and they are stowed. Some of the companies are stowing those rotors and trying to stow them in a less draggy way, but we focused on the lift over drag of these vehicles to try to minimize the drag of the vehicle. So while separate lift thrust VTOL is the most popular, it's got its downsides. But the cons of some of these vehicles, I'll just try to be upfront about it, is everybody who works in VTOLs know that tilt wings they're very difficult, and they take a while to tune and get through the transition phase. But we spent a lot of time on that and worked through the transition of the GL10 vehicle, and we have a pretty reliable transition methodology worked out for that vehicle. And then the trifecta, that's a tilt rotor vehicle, which doesn't, well, another downside of tilt wings is that in crosswind conditions, they can, if you don't have enough control authority, they can have yaw problems and heading problems. But the trifecta vehicle is not a tilt wing, it's a tilt rotor design, so it doesn't have as many of the problems in that aspect.
All right, so this is kind of a two-part question. It's from the same person. What, if any, software is included if someone were to license this technology? And is there a bill of materials included, or that you could include, as part of the license?
Okay, so first question, like I said, it's an off-the-shelf flight controller and off or open source firmware, and that you can literally go to the website and download that stuff, and we could get you that the location of that firmware. But if you just did a search on Open Aero VTOL, you would be able to find that firmware pretty easily, and then it would also tell you about the control board too. And then the second part of that equation was the drawings. I believe we discussed this in our last meeting, and the answer was yes, we do have drawings, and I do believe they would be available as far as I know.
How about a list of materials too?
And that's for the GL10. The trifecta vehicle, there is not a set of drawings for that. That was actually built from specs and in cooperation with our model shop, and that was done without a full set of real engineering drawings. But the GL10 does have a full set of engineering drawings.
Great. This is always a tricky question because people ask it a lot. Do you have an estimate or an expected cost for manufacturing one of these vehicles?
Ooh, that's a good one. I really don't. It's, less than $1 million, but more than $10.
There you go. So maybe something to talk about later when we're in more serious discussions about licensing.
Yeah.
Going back to the COTS, does the GL10 use COTS actuators?
Yes, they do. Everything on the GL10 except for a few, of course, all of the molds for the fuselage and wings were all custom molds, but every other part, like motors, actuators, they're all commercially available. There were a few parts that we machined in, like the middle of the wing spar has some bracketry on it that was machined in our machine shop, but everything else is mostly COTS hardware.
Great. Well, we're working through them, and we're almost at the end of our questions. So if you have any more out there in the audience and you'd like to submit them, please do that now. If we don't get to any question that you've asked today, we will definitely follow up by email. But if you have any more that you'd like to submit, please do that in the chat box now. So the last question I have in the queue right now that I think is one that we could talk about is, there's been a lot of talk recently about this Uber and NASA collaboration and a vehicle made from that. So how do you see this kind of fitting into that air mobility, urban air mobility type of vehicle?
Well, either of these concepts, I think, with some development work, could be used for urban air mobility, particularly for the unmanned part of urban air mobility. I don't know if this person's question is about manned urban air mobility, but NASA defines urban air mobility as both smaller unmanned vehicles that would do things like carrying packages and all the way up to manned vehicles. So either of those applications, I think, work for these vehicles. There would definitely need to be some development work done if they were applied to manned flight vehicles. For the unmanned, like package delivery stuff, I think the designs are right there. I mean, you can deliver a 5-pound package with the smaller 50% 10-foot wingspan vehicle, or if you wanted to deliver bigger packages, you could go with the 20-foot design. But either of these designs is amenable to urban air mobility applications.
Great. All right. So we got one more. And then I think this will be our last question. And again, if we didn't answer your question, then we will follow up with that afterwards. There are a couple in there that I think are very specific, and I want to leave them for a direct answer via email. But regarding the software tuning and the configuration settings that you developed during this, was that something that could be made available to a company that were to license this?
Sure, I believe so.
Okay.
About a little more detail about that, we are not saying that we optimize those flight parameters enough to do what we wanted to do, which is get the vehicle through its flight testing phase, first flight testing phase. So we're not claiming that these control parameters are optimized in any way. They were just sufficient for what we wanted to do. So I just wanted to characterize that. But the answer is yes. I think those settings for the OpenAero VTOL code are available to you.
All right. Well, great. Thank you, David. Thank you, Jennifer. Thank you, everyone in the audience, for being here today. Again, there are a few questions there that we didn't get to, but we will answer you within the next week or so via email. If anyone out there has additional questions, because I'm sure that they're going to come to you after thinking about it a little bit, please feel free to submit those to the email address that you see on the slide at the bottom there, the LARC-DL Technology Gateway, and we will get back to you very quickly with answers to those as well. Once again, we really appreciate you attending today's webinar, and look out for more information via our mailing list on future webinars. Other than that, have a great day. Thank you.